We're going to finish off the first chapter, linear systems, by another application, the temperature of a plate, the equilibrium temperature of a plate. Now, what I want to stress here is like the problems are kind of small, um, and kind of why are we doing this section? It's a kind of a combination of seeing a type of linear system that's actually easy to solve, or rather approximate the solution of. And the other idea is that you can chop a complicated component. Now we're actually not looking at a very complicated component, but you can chop a complicated component up into little pieces and kind of analyze them on that level, and sometimes that can make things easier. That's called discretization or finite element analysis. So that's really what I'm interested in here rather than the temperature of a plate. But we'll pretend in this section anyway that you do care about such a thing. It's like some of the things we say here will be true. So I say many of the structural properties of material are thermal. They vary with temperature. So you might be interested in the temperature distribution of a structure. So how does the temperature move in it? So this one is a kind of a silly made up examples, but we'll look at it. So you got a dam here. This is the dam. And you've got a fair amount of air, you got the sun or what have you. And then you've got a large body of water. Which could be colder than the air. And certainly if I won't bother with brown, but I have orange, and then you've got a load of earth. Now I'm not sure, as it happens, how does cement or whatever. Well, I suppose there'd be more than cement in a dam, I presume. Something like this. So you want to get the temperature distribution in the dam, like yeah, because you want to, yeah, this kind of thing. Now whether that's realistic or not, I don't care. I'm a mathematician. So what we're going to do is we're going to consider a simpler two-dimensional problem of a plate. Now, if there's different boundary temperatures, we're probably just going to use constant. So we'll call this T for top, T R for right, T B for bottom, T L for left, something like this. If the boundary temperatures are held constant for enough time, like so, for example, if the plate is initially cold and say the bottom temperature is hot, you're going to get a heat transfer from the bottom boundary into the plate, and it's going to keep on moving until you reach an equilibrium. I don't know if you're aware of this. I don't know how much thermal stuff you do, but anyway, this will happen. And the question is to find the equilibrium temperature distribution for all points on the plate. Now that's kind of difficult. You have to solve a pretty tricky partial differential equation, which I think is the partial derivative of t with respect to the horizontal distance, second derivative, plus the partial derivative of temperature, second partial derivative with respect to the vertical distance is equal to 0. No joke solving that. Absolutely no joke. I don't even really know how to do it. So it's a difficult problem. And this one you can do it. I mean, there's boundary temperatures and they're constant. But if the thing was more complicated, you're in an awful situation, right? However, what we can do instead is consider just a few points of the plate. So this is discretization. So you could chop this up into pieces. Now they should be square pieces. I don't know if they'll be square by the time I'm finished with them. Pretty not good actually. They should all be squares. That's probably a bit better, yeah. And what we'll do then is we'll, rather than kind of getting a formula for the temperature at all points, which is difficult, we'll get the temperature, say here, and here, and here, or rather, we will approximate the temperatures there, and there. Okay. Now, how we can do this is you have something called the mean value property. So if a plate has reached thermal equilibrium, if you have a point on the plate, that's supposed to be a circle now, by the way. So if this is point T, so we're talking about, say, the temperature at point P. it turns out that if you draw a radius around this thing, that the temperature in the middle is the average of the temperatures on the circle. Now, how you do that is no joke also, and I'll write down, strictly speaking, something I think that I shouldn't really even try, but basically, yeah, I'll just write, so the temperature P, you see the point is how do you average over infinitely many things. You would have done this a little bit in Math 60/40, but look, I'm kind of spending waste when you find the mean, or actually it was first year, but we don't want to spend too much time on this. So the temperature here is the average over the circle. The temperature is on the, just the average temperature over all the points of the circle. So let's say this is a coordinate XY. There. Yeah, if you're really interested, you can Google how to find the average of infinitely many numbers. It can be done. Sounds a bit contradictory, but it can be done. And this thing I've written here, the mean value property, the mean just means average. It stands to reason. I mean, think about standing in a room and putting your hand up. Imagine if kind of on the right hand side of your hand is warm and the left hand side of your hand is cold, and say the rest of it's kind of, somewhere in between. Isn't the temperature of your hand is going to kind of be the average of all of those? Like if you've hot and cold, right and left, you're going to be somewhere in the middle. Okay. So what we're going to do is we're going to make this approximation even simpler. We're going to say if a plate is partitioned into grid points an equal distance apart, like we did up here, then the temperature at an internal grid point is equal to the average of adjacent grid points. So I'll show you how this actually, the idea here. So if the true solution, in other words, the true solution of this partial differential equation at the point where T1 is, the temperature there is the average of these. That's the average of infinitely many temperatures. So what we're going to do is we're going to make it simpler by, rather than taking the average of infinitely many, we're just going to take the average of the temperature here, 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 here. So the purple bit represents theoretically how you could find, well, it ends up, if you write down the mean value property, you end up with this equation on the left with the partial differential equation. So in a way, this does define the exact solution. So you have an average of infinitely many points. So we're going to approximate essentially the equation on the left by saying that rather than finding the average over all the infinitely many points in the circle, we'll just go over 4 of them. So you'd say that T1 should be equal to, so the top node is the top temperature, plus T2 is the temperature to the right, plus T bottom is the temperature in the bottom, plus TL over 4. Now, in terms of what's going on here, this is a variable, and this is a variable, but these other temperatures are constant. And what you do is you write a similar equation for T2 and a similar equation for T3, and you end up with 3 equations and 3 unknowns, suggesting that there's a unique solution, as there should be, of course. And what we're doing really is we're approximating essentially the exact equation. So we're essentially approximating the equation. That's what we're doing. Okay. We'll do some examples. As the numbers are going to be nasty, we could use rounding to a number of significant figures along with partial pivoting. Okay, so what I'm saying is you write down these linear systems, these simultaneous equations, you end up with nasty numbers. So you say, okay, we won't do exact arithmetic with fractions, we'll do partial pivoting instead. But in fact, there's an other easier method altogether. Linear systems where the equations of this form we're going to learn are very, very simple to analyze indeed. Now, you might be confused. How is this a linear system? Well, let's just do a little. So just taking from this, I just need some space here. So suppose the top temperature was, say, 0, and suppose the left temperature was 20, and suppose the bottom temperature was 80, then what you could show is if you multiply both sides by 4, you get 4t1 variable, take away t2 from both sides, minus t2 variable equal to constants, top temperature plus bottom temperature plus left temperature, I get 100. So these things do give you linear equations, multiple of t1 plus multiple of t2 plus multiple of t3, in this case 0, equal to a constant. So you get 3 of them, you do get a linear system. And what I'm saying down the bottom is these are what are called diagonally dominant. Diagonally dominant means that when you write down this equation for t1, you see this 4 here, it's bigger than the multiple of minus 1. If you write down the equation for t2, you get a big number, t2, and the other one you get a big number. Imagine if these numbers were really, really big. Like imagine if this number was like 4,000. Then it doesn't really matter what t2 is, because 4,000 times t1 surely dwarfs it. So you just get 4t1 is equal to 100, and then you kind of get an easy approximation like that. And it turns out that these linear systems are really well behaved. And even when you've got loads and loads and loads of unknowns, which means loads and loads and loads of equations, it's reasonable to solve them on a computer very easily, which is not the case for Gaussian elimination. So we've already seen examples that behave badly, that are ill-conditioned. So that's when rounding is a problem. A class of matrices that are well behaved are diagonally dominant. And what you'll see is the pivots are all going to be big numbers, essentially. Okay, so a diagonally dominant matrix is one whose diagonal element is larger in magnitude than all the other ones put together. So for example, so let's do one here. So say if this was, say, 2 and minus 3, then this would be bigger than 2 plus 3. So that'd be 7. Say this was 0.1 and this was 0.8. The middle number should be bigger than 0.9. And say this number is, say, whatever, 5, and this one is minus 4. This one should be bigger than 9. So this is a diagonally dominant system. And so you're kind of going to end up, if you were to do Gaussian elimination, you're not going to get small pivots. So it's well behaved. Now, there's a thing here, and I can go through this and you can read it yourself, right? But to be honestly, it's actually, now you realize, from that, I like to show you the theory, but it doesn't really add much. So I think we're better off just doing an example. Now maybe we'll do something. So we'll just explain. So now we're going to a vector. So t. So you're going to start with t0. That's an approximation. So the idea is that, let me get my notation right. Oh, I can't remember my own notation. So this 0 indicates it's initial. So it'll be like t0, the first temperature. Mess it up now. I think I'm going to call it t0. Yeah, so t0, 1, and you're going to have a few temperatures, say n of them. So you start with an approximation of the temperatures, and what you're going to do is you got the equations, and you're going to feed them into the equations. You'll see this in an example, and you'll get out a better approximation. So we'll call this T1. So that's the first approximation, first iteration, second approximation is temperature 1 up to the first iteration of temperature n, and you keep feeding it in. So you're getting these. So this is what I'm saying is, say on the original one, you're going to start with a guess of the temperatures of T1, T2, T3. You're going to generate a better approximation, and then you're going to generate a better approximation, and you're going to keep doing this, and it turns out that this converges. So if you keep going, if you go infinitely many times, say we call it T infinity, now what you get here is the exact solution of the approximate equations. So exact solution of approximate equations. Now, why are the equations approximate? Well, because we're not summing over all the infinitely many points to average. we're just taking 4. So the equations are approximate, but we end up with exact solutions. Now, the other thing that's unfortunately true is that we don't have an infinite amount of time. So we'll stop some stage. And so we'll stop maybe here, say somewhere in here. Stop when kind of you're not getting much of a difference. So say when the k plus 1 approximation is pretty much the same thing, we're going to stop. Now you can get, I teach this as well to mechanical engineers, and you get into a world of pain kind of saying, when should you stop? But we're going to stop when we get kind of agreement twice in a row. Now things can go wonky because things can kind of slow down and then change again, but we won't worry about that. So the idea is guess the temperatures, put them into some equations, you get out better guesses. Put the better guesses into the equation, you get out even better. And as you keep putting them in, you get better and better and better approximations. And in the limit, as you do it infinitely many times, you get the exact solution of the approximate equation. So if you stop here, when you get similarity twice in a row, you have an approximate solution to the approximate equations. But the approximate solutions are pretty good, the approximate equations not really. Okay, so there's all this formula like this. This is kind of saying these are these approximations. We could probably do these with, yeah. Look, let's just do an example. Okay, trust me, it's easy. This is easy. It's the easiest thing to have in this module. Might be the easiest thing you do this year. Right. So the following plate has dimensions 3 to 2 and is subject to boundary temperatures as shown. So the first thing we'll do is grid it up. So the 3 refers to the columns and the 2 is such to the rows. So there's your 2. 3. That's what I mean by 3 to 2. I probably should read the question. Using an appropriate grid, there it is. Find a linear system whose solution approximates the heat distribution of the plate at internal grid points using the mean value property. So all I'm saying is we've got 2 variables. Now you can call these x and y if you want. I prefer T1, T2. So we're going to write down T2 is the temperature there. We're going to say that the temperature at T1 is the average of the 4 grid points. And the temperature at T2 is the average of these 4 grid points. And they're approximate equations, and then we'll solve them approximately. So we've gridded up, right? And now let's write down our mean value property. So T1 is equal to the average of the stuff that's around. So on top of T1, I see 10. To the left, I see another 10. On the bottom, I see 30. And we also have T2, which is another variable, divided by 4. And so you get T1, 10 plus 10, 20, plus 30, 50. T2 plus 50 divided by 4. And the thing is, what's going to be nice is now I will write them up just as a matrix equation above, as you'll see, but we won't be actually doing that. And then T2, what's the adjacent? So on top we have 10, to the right we have 30, and to the bottom we have 30, and to the left we have temperature 1, and that is to be divided by 4. And so we have another equation, T2 is equal to T1 plus 30 plus 30 plus 10 is 70 over 4. So the equations I referenced are these. Now you can go away and write this as a matrix equation. You can write this as, if you really wanted to, I think it'd be 4T1 minus 1T2, and you'd have minus 1T1 plus 4T2 and then I think the numbers would be 50 and 70, I think. But we're not going to go to that, like, I mean, so I'm saying, oh, you go to this. But what I'm saying, don't go to that. What I want you to imagine is that we cut it actually up into loads of pieces, not just 2. And that means like this Gaussian elimination becomes quickly out of, is not an option. If you've loads of equations, that's not an option. But use these equations down here instead. So we're going to find the first approximation. Now you can actually do whatever you want for the first approximation. We'll give you some possibilities. So So these are for our what I'm calling T1, 0. The 0 means kind of initial, and T2, 0, these initial guesses. So here's some examples. You could take both of them starting at 0. It turns out that no matter where you start, if you keep feeding, so you're going to be feeding in approximations into these equations below, you get a better approximations. And it turns out it doesn't actually matter where you start. So if you start at 0, that's as good as any. I think it's probably better just to give it a bit of help. So if you're to give it a bit of help, what you would do is see the T1, look at the average of the ones around it, 10 plus 10 plus 30. Now you don't know T2, so leave that one out of it. So you get 50 over 3. Now I'll probably be recommending something about significant figures. So it says 3, so it's 16.666, 16.7. And that's probably what we're going to go with, by the way. And then T2 will be roughly the average of 30 and 30 and 70 and 10, excuse me, which is 23.3. Okay. Another option could be, I said the thing earlier on where the T1 is dominant. So you can kind of just forget about the T2. And if you do that here, just forget about this T2. You get 50 over 4. What's that? 12.5, is it? Yeah. And do the same to the other one. I think you get 17.5. Another example again is you could take the average of all of the boundary temperatures. So 10 and 10 is 20, plus the other two you get 80. So you start them all off at 20. Now you can do whatever of these you want, whichever one makes more sense to you. Personally, I think this one makes the most sense. You're just taking the average of the things you know about. Okay. So we'll take this as our very first approximation to the temperature. So we're taking what we call T10 equal to 16.7 and T20 equal to 23.3. Now the thing here, we've made a big deal about rounding before. Here we're not making any deal. We wrote in the previous page that when the matrix is diagonally dominant, as this is, they're well conditioned, so you don't have any problems with rounding. So rounding just isn't really an issue. Okay, so I probably should write approximations here. Well, actually, no, these are equals. So you kind of got a thing where this is an approximation to T1, which is the solution of this equation, which is an approximation itself to something. So there's approximations on top of approximations. Now what we're going to do is we're going to lob in these numbers here into these equations, and we're going to get better approximations. So I'm going to pause and just write down the equations for myself. So just before we go to the next page, be clear what we're going to do is we're going to see the T1 here, we're going to put that in here, and we're going to put the T2, the 23.3, in here, and that's going to give us a better approximation to the solution of the linear system. And we're going to keep on going until we kind of get the same thing twice. Well, that's what we should do, but this actually just says use 2 iterations, so just do it twice. Okay, so we have our first approximation, we did that. To find the second approximation, we throw these into the equations above. So this is what we're actually calling T0. So the first iteration, the temperature 1. Now the equation for temperature 1 is temperature 2 plus 50 over 4. So I put in the previous temperature 2. So it'll be temperature 2 plus 50 over 4. And it says use 3 significant figures, so I'll do that. So I do 23.3 plus 50 divided by 4. I get 18.3. And now let's do the first approximation, first iteration to temperature 2 equal to. So the formula is temperature 2 plus 50. Oh, I'm an idiot. No, I'm not. Temperature 1 plus 70. So temperature 1 is 16.7 plus 70 over 4. And then this is equal to 3 significant figures. I get 21.7. Now, there's one comment we could make here. So this is called the Jacobi method for solving diagonally dominant systems. See, at this point you have 18.3, and we know that that's more accurate, because that's what we're saying, that this is a better shout than 16.7. If you were to throw that in there, the very, very latest one, that's called Gauss-Seidel. And if you do that by accident, it's not going to be the end of the world, but we're going to do it with the Jacobi method. So we put in the previous value. Now anyway, we go again. So we're looking at the second iteration to T1. Now the equation for T1 is T2 plus 50. So we put in the previous T2, which is 21.7, plus 50 divided by 4. And let's look at this to four significant figures. 21.7 plus 50 divided by 4. I get 17.9. And then the other one, so the second temperature, the one on the right, second iteration is equal to, now the formula for this is temperature 1 plus 70 over 40, and the previous temperature 1 is 18.3 plus 70 over, not 40, over 4. So what do we get? 18.3 plus 70 divided by 4, 22.1. Now look at what I want you to look at here is the difference between these. So I'm just going to write a delta here. Delta 1 is the difference between the initial approximation to temperature 1 and the second one. So you're going from 16.7 to 18.3. That's at 1.6. And for the second temperature, what is the change? And the first one, you're going from 23.3 to 21.7. It's the same, 1.6. Now, I don't think it's guaranteed always to be the same. Maybe I'll learn that it is. Then the second difference and the first temperature, you go from 18.3 to 17.4, that's 0.4. And then over here, the second temperature, the second difference, you're going from 21.7. Oh, it's actually, I don't know, it must be always the same. And actually, if you want, you can imagine this as like a flow of heat. Like if you actually look at the one on the left, it's getting colder, and the one on the right is getting warmer. And you can think of it like that. In a certain strict sense, I've got a long post, I don't know if I'll put it in the thing, that actually explains that if you start the plate off at the initial temperature, this is how it would actually heat up with some fairly heavy maths. So what we're ending up with is that these differences in temperature, which are actually little bits of temperature heat transfer, they get smaller and smaller and smaller. So it's gone from 1.6 to 0.4, and it'll get smaller and smaller and smaller. And so eventually these things converge to the exact solution of those approximate equations. So we'll just look where we are at the moment. 17.9, 22.1. 17.9, 22.1. What can we say about this? Well, we can say that this is better than what we started with, but it hasn't converged. Like if you look at it, the differences are still 0.4, and they could change for quite a while. So even though an exam question, I'll ask you just to go twice. Of course, we don't have an exam, so you'll have to see what the assignment says, but in theory, you should keep on going until you get the same answer twice in a row to three significant figures. Okay. Another example here. Now, this is a 3D box, but the maths is pretty much the same. So consider an uninsulated 3D box in the ratio 4 to 2 to 2, with left temperature 100 degrees, that's there, right temperature 20, and boundary temperature 0 in the middle is shown. The mean value property also holds for equilibrium temperature distributions in 3 dimensions. So that's like the hand. It's like the average temperature of the sphere around it. Therefore, if the box is divided as shown, we can approximate the mean value property for T1, T2, T3 by averaging over the 6 adjacent points, and this gives these equations. So this question is great. It's given us everything. I'm going to pause and write down those equations. So let's see what else the thing says. Using the initial temperature, now it's giving us 20, 0, and 4. Now, where are they coming from? I think the 20 I think there's 5 adjacent temperatures to T1 that are known. So there's this face, that's 1, up here that's 2, over here that's 3, and down here that's 4. They're all zeros. So for T1 the adjacent temperatures are just 5 zeros and 100. So that's 100 divided by 5 is 20. The only things adjacent to T2 that you know about are all zeros. If you can see what I'm doing. And T3 you end up with 4. So that's where those numbers are coming from. I might ask you to come up with your own first approximation, or I might give you one. Use 2 iterations of the Jacobi method to approximate the solution of the linear system. Use 4 significant figures. So we're going to bang in. I've written down the equations, and now what I have to do is bang in. Okay, so let's go. So the first, so we got temperature 1 there, the first iteration of the Jacobi method. So it's T2 plus 100. T2, the previous T2 is 0, plus 100 over 6. I think we'll have space here, will we? 100 over 6. Do we say 4 significant figures? 16.67. Next one. The second temperature, first iteration. So that's T1 plus T3 over 6. The previous T1 is 20. The previous T3 is 4. Remember to pause me if you need to. It's 24 over 6, so that stays at 4. And then the next one, T3, 1. And the last one, so the equation for T3 is T2 plus 20. Previous T2 is 0 plus 20 over 6. 20 divided by 6 is 3.24 significant figures. Yeah, this is 0, 0, 0. And 3.333. So now we feed them into the same equations again. So the second iteration for T1 is equal to T2 plus 100 over 6. The previous T2 is 4 plus 100 over 6. We'll do maybe all the calculator at the end. I don't know, we'll do it here. 104 divided by 6. I get 17.33. Okay, and then the second iteration to the second temperature is equal to, so the formula on the previous page is temperature 1 plus temperature 3 over 6. The previous temperature 1 is 16.67. The previous temperature 3 is 3.333 divided by 6. I think that's going to be the same thing. What am I talking about? Nonsense. I get 3.334 if I look at it carefully. And then the other one, the third temperature, second iteration. So this is temperature 2 plus 20. Previous temperature 2 is 4 plus 20 over 6. And I get 4. So you get this weird thing where the temperature is kind of, it's a bit weird. You're getting a flow of temperature from the left to the right. Okay, but that's it. Then part B, has the Jacobi method converged? So have you got the same answer twice in a row? And the answer is no. You need them all to converge. Now none of these have converged because they're all still changing. This is 16.7. This is 17.3. It's still changing, so it is not converged. Okay. Any more questions on this? No, I don't.